Have you ever, typed a prompt into a large language model, given it just a couple of examples, and then watched it just do something new, something you never explicitly trained it for?
Yeah, it feels almost like magic sometimes, doesn't it? Like it just gets it instantly.
Exactly. We call this in-context learning, or ICL. And it's one of the most amazing things about modern
It
LLMs.
really is.
But here's the burning question that kind of lingers. Is what we're seeing true actual learning, or is it maybe something else going on?
That's the million-dollar question, isn't it?
Today, we're taking a deep dive into a really fascinating and, frankly, incredibly rigorous study. It's from Adrian de Winter and his team over at Microsoft and the University of York.
Mhm.
Their paper is called, very directly, is in-context learning. And they
No.
don't just, wonder about it. They tackle it head on with this huge empirical analysis.
Yeah, the massive piece of work. And our mission for you today really is to help you get a clearer, maybe more nuanced understanding of what LLMs are truly capable of when we talk about learning. We're going to unpack the formal definitions of learning from learning theory, compare that to how LLMs actually do in-context learning, and then dig into the, well, pretty surprising findings from this big study. You might find your whole perspective on LLMs shifts a bit after this.
Okay, so let's unpack this core idea first. What exactly is in-context learning ICL, beyond just, giving it examples in the prompt?
Well, at its heart, ICL lets these autoregressive LLMs, the ones that predict the next word, basically solve tasks without needing any permanent updates, no changes to their internal knowledge or weights.
Okay, so not like traditional training.
Exactly. Think of it like this.
Yeah.
Usually a machine learning model learns by adjusting its internal settings, its brain, you could say, to encode what it sees.
Right, it stores the information.
With ICL, the LLM's fundamental knowledge, its weights, they stay frozen.
Mhm.
Instead, it uses its existing knowledge combined with the examples, the exemplars you give it right there in the prompt.
Ah,
It's like it updates its beliefs sort of ad hoc right then and there, figuring things out based purely on that specific conversation.
so if I'm getting this right, it's less like adding a new recipe to its permanent cookbook
Yeah, good analogy.
and more like a really brilliant chef who can just improvise an amazing meal with whatever ingredients you hand them right now, but they don't necessarily remember that exact combo later,
That's a great way to put it. It's dynamic temporary knowledge application.
which is a really crucial difference from traditional machine learning.
Absolutely. And this brings us right to the core debate that the study frames so well. Knowing is not always the same as learning.
Mm-hmm.
In formal learning theory, real learning boils down to one key concept: generalization.
Generalization, okay.
A learner sees data from one situation, one distribution, let's call it flavor P, encodes that somehow, and then, crucially, should be able to apply that knowledge to new unseen stuff, maybe from a different situation, flavor Q, with some guarantee, like a bounded probability of making mistakes.
Right, it needs to work beyond the exact examples.
Precisely. Now, the study argues, mathematically, that ICL does fit within a reframed pack. Probably approximately correct learning framework. So it has a formal basis as learning. It can be approximately correct with high probability.
Okay, so technically it is learning.
Technically, yes,
Yeah.
but the real question is about the effectiveness of that learning.
Oh.
How well does it actually generalize from P to handle Q? That's what needed this huge empirical investigation.
Which really gets to the heart of it for anyone using these models. Is ICL this robust way to truly generalize, to understand the underlying rules? Or is it more like a super clever deduction trick that just finds patterns in the immediate prompt?
That's exactly what this massive study aimed to figure out.
And when we say massive, we really should emphasize that this wasn't just, a few quick tests.
No, not at all. To get at these really deep questions, they went all out. This reflects some serious scientific rigor.
So what did they actually do?
Well, get this. The study involved a staggering 1.89 million predictions, and that's per LLM.
Wow, per model.
Per model. They looked at 4 big ones: GPT-4 Turbo, GPT-4o, Mixed Rule 8x7b Instruct v01, and Phi 3.5 MOE Instruct. So a good range of current models.
Okay. And they weren't just testing one thing, right?
Not even close.
Yeah.
They explored 9 different tasks. These ranged from foundational problems in formal language theory.
Like logic puzzles.
Sort of, yeah. Things that test basic computation. But also more practical, everyday type scenarios that probe different cognitive abilities.
And these tasks, they were designed to push the models, I assume, not just easy stuff.
Definitely. They included problems that can be solved by what we call finite state automata, or FSAs. These are like simple machines with limited memory. They only know their current state.
Okay.
Think of tasks like parity, deciding if a string of zeros and ones has an even number of zeros, or basic pattern matching. Simple rules, limited memory needed.
Right.
But then they also threw in more complex tasks, ones that need a kind of operational memory, solvable by push-down automata, PDAs, which are like FSAs, but they have a memory stack.
Ah, so they can remember more context.
Exactly. Like the reversal task, checking if the string L is the reverse of string R when you see L chart, or task involving stack manipulation. These need memory.
Gotcha. Different levels of complexity.
Precisely. And they didn't just vary the tasks. They also meticulously tested 7 different prompting strategies.
7. Okay, like what?
Everything from simple end-shot learning, just giving examples, sometimes called modus ponens if there's no system prompt, and description-based prompts, to more sophisticated things like automated prompt optimization, APO, where the system tries to find the best prompt itself.
Right.
And of course, chain of thought, or COT, which tries to make the model show its reasoning steps.
But one everyone talks about.
Exactly.
Yeah.
And crucially, they even threw in these wildcard prompts, things like word salad, where the system prompt was just random, nonsensical words.
Seriously. Just gibberish.
Pretty much.
Like,
and salad of thought, or SOBR, which randomized the examples within a chain of thought prompt. The idea was to isolate the impact of the language itself versus the underlying data patterns.
that's clever. Trying to see what the model really pays attention to.
And maybe the most impressive part is how they generated their data. They created synthetic data sets for every task, carefully controlling the probabilities.
Why was that so important?
To meticulously set up in distribution, or ID, scenarios where the test data looks like the examples, and out of distribution, ODE scenarios where it looks different, that's absolutely vital for testing true generalization.
Makes sense. You need to see if it works on stuff it hasn't seen before.
Exactly. And they even deliberately mislabeled 5% of the data entries
Why do that?
to explicitly test for simple memorization versus actual learning. It sets a kind of theoretical maximum accuracy, 95% for any true learner on their data. If a model gets higher than that, it's probably just memorizing.
Wow. That's incredibly thorough control. Allows them to really probe generalization, not just recall.
Precisely. Rigorous stuff.
Okay, so with that super rigorous setup in mind, let's dive into the results. Because some of them are really eye-opening, right? Especially around this whole few-shot learning idea.
Oh, absolutely. The common story, which you hear all the time, is that LLMs just need a few examples, right? Few-shot learning. Magic.
Yeah, that's the narrative.
Well, this study pretty much blows that out of the water, or at least complicates it hugely. One of the most striking findings directly contradicts that.
Okay, what did they find?
Instead of needing just a few examples, they found that peak average performance across tasks was actually observed when the models were given 50 to 100 exemplars.
50 to 100, not 5.
Not 5, no.
Yeah.
50 to 100. So for reliable performance, few shot often actually means many shot.
That's a massive difference. It really changes how you'd think about prompting reliably.
It absolutely does. It suggests that if you're under-resourcing your prompts with examples, you're likely going to get pretty inconsistent results. You need volume for reliability.
Okay, that's a huge point. And then it gets even more interesting, right? About what happens with lots of examples.
Yes. So in the limit, basically, as the number of examples kept growing, the study found something fascinating. Accuracy started to become surprisingly insensitive to things we'd normally assume are critical,
Like what?
like the specific way the examples were distributed, which exact LLM model they used, the particular prompt style,
Even chain of thought versus simple examples?
even that, and even the surface linguistic features of the input. In the limit, with enough data, those differences started to matter less for overall accuracy.
So what does that suggest is actually happening?
It suggests that with enough examples, the models stop relying so much on those superficial cues. Instead, they start deducing patterns from the inherent regularities within the prompt data itself.
Ah, the signal and the noise.
Exactly. The how of the prompt, the specific wording, the model choice seems to matter less than the sheer volume of what you show it. They found all prompting strategies steadily improved accuracy with more shots. It points to this ability to extract underlying patterns, but only when the volume is high enough.
Okay, finding one. More shots are generally better, often many more than we think. What's the next big surprise?
Well, the next one is about task variability. And this could be a real aha moment for you listening. You might think, okay, if an LLM can solve one kind of logical puzzle, it should be pretty good at a similar one, right? It sort of learns by analogy.
Yeah, that seems intuitive.
Turns out, not necessarily. This study found huge inconsistencies in performance, even across tasks that seem really closely related.
How inconsistent are we talking?
We're talking major differences. For example, pattern matching, that simpler FSA task, they got it working really well, like 94% accuracy.
Yeah.
Impressive.
Okay.
But then vending machine, this arithmetic task that needs the model to track a running total, kind of simple memory, accuracy plummeted to just 16%. 16.
Wow, from 94 to 16 on tasks that both involve symbols and state.
Exactly. It's a huge gap for things that, on the surface, might seem like similar computational challenges for an intelligent system.
And this wasn't just a one-off.
No, they found this pattern more broadly. Get this. Closely related tasks did not necessarily lead to closely related performance. They saw average accuracy gaps between seemingly similar tasks as large as 31%.
31%, that's massive.
It is. Think about pattern matching versus maze, solve. Both kind of involve navigating symbols or paths, right?
Yeah, seems related.
Yet the performance difference was huge. It's like teaching someone to be brilliant at Sudoku doesn't automatically make him great at chess. The underlying logic, while maybe related conceptually, is processed very differently.
That really challenges the idea of these models having general reasoning ability sometimes.
It certainly complicates it. And here's another kicker. They compared ICL performance to traditional, simpler machine learning baselines, things like decision trees, k-nearest neighbors.
Oh, old school ML.
Right. And those simpler baselines actually outperformed ICL's average performance in half of the tasks they evaluated.
Half the tasks. So ICL isn't always better?
Not always, not on average, across these tasks. It really puts the LLM's capabilities into perspective. Their generalization isn't universally superior. And that distinction we mentioned earlier between the simpler FSA-level tasks, like parity, and the harder PDA-level tasks needing memory, like reversal or stack manipulation, that seems to be a key factor.
So the memory requirement trips them up.
It seems to. LLMs, because they predict the next token, can sort of simulate a memory stack by using their own output. They can act like PDAs.
Right.
But their ability to actually leverage that effectively and consistently, it varies wildly. It's not a given, even if they technically can do it.
Okay, so finding 2. Performance is highly task-dependent, surprisingly inconsistent even on related tasks, and not always better than simpler methods, especially when memory is needed. What about the ultimate test dealing with the truly unexpected?
Ah, yes, the out-of-distribution problem. How does ICL handle situations that are genuinely new where the data doesn't look like the examples it saw in the prompt?
This feels critical for real-world reliability.
Absolutely. And this is where the limitations of ICL really become clear.
How so?
Well, first, the good news, sort of. ICL turned out to be pretty robust if you mess with the training examples themselves. Like if you shuffled the order of exemplars or used imbalanced sets where one answer appeared way more often. And the limit, with enough examples, performance wasn't hugely affected. It could handle noise in the input examples reasonably well.
Okay, so it's stable in that sense.
Yes. However, it proved to be remarkably brittle, very fragile, when faced with altered test distributions, especially as the distance or difference between the training examples and the test questions grew.
So the OD scenarios we talked about?
Exactly. When the questions started to look different from the examples, ICL struggled significantly. It couldn't adapt well to that true novelty.
And didn't you say some prompting strategies actually made this worse? That sounds backwards.
It does sound backwards, but yes, that's a critical finding.
Right.
Remember chain of thought, explicit, and automated prompt optimization, APO, more sophisticated strategies.
Yeah, the ones meant to improve reasoning or find the best prompt.
Well, while they are powerful for problems that look like the examples in distribution, they turn out to be the most sensitive, the most fragile, when faced with these OG shifts.
Wow. So the smarter prompts were worse at generalizing?
In this ODE context, yes.
Yeah.
It seems their sophisticated reasoning steps, or the prompts they optimize themselves to find, end up biasing the learner too strongly towards the specific patterns seen in the examples.
They overfit to the prompt examples, basically.
That's a good way to think about it. They become less adaptable to true novelty. This isn't just a minor issue, it suggests a fundamental limitation. ICL is strong within its comfort zone, but can be like a house of cards when faced with genuinely new situations, especially when using techniques like coding that we think enhance reasoning.
It implies that this ad hoc encoding, figuring things out on the fly from the prompt, it just isn't a robust mechanism for true ode generalization.
Precisely. It highlights this critical difference between solving a known type of problem very well and truly adapting to a genuinely new one.
Okay, this all leads to the biggest question, really. Why? Why these limitations? What's actually going on inside these models during ICL that leads to this brittleness?
That's what the ablation studies try to get at. Remember those word salad experiments?
Yeah, where they used random words in the system prompt. Seemed crazy.
It did. But the results were fascinating. They found that while performance took an initial hit, with enough examples, the models using word salad prompts often reached accuracies near or sometimes even matching the ones with normal, sensible prompts.
So they learned to ignore the gibberish.
It suggests they can, yeah. To some extent, they seem able to distinguish the important underlying data features, the actual task pattern, from the superficial lexical features, the specific words in the system prompt. They can filter out that kind of noise eventually.
Okay, that makes sense. But then, what about the other salad experiment? The salad of thought.
Ah, yes. And this is where it gets really interesting for you listening. When they didn't just randomize the system prompt, but randomize the exemplars themselves within a chain of thought prompt.
So the examples became nonsense.
Exactly. Random words standing in for the examples and the reasoning steps. Performance absolutely tanked. It plunged to the lowest average accuracy they saw, around 23%.
Okay, wait. So the model can ignore random words in the instructions, the system prompt, but not random words in the examples. Why is that distinction so critical?
Because the exemplars are where the model finds those statistical patterns it needs to latch onto. That's the input data for its ad hoc learning.
Right.
If those patterns themselves are randomized, if the examples are just noise, there's nothing meaningful for it to deduce the underlying logic from. It can't find the signal.
So it relies heavily on the patterns in the examples.
Extremely heavily. And this finding really supports the study's main conclusion. ICL tends to overfocus on spurious statistical features it extracts from the prompt examples. It gets really good at mimicking the patterns it sees. But it doesn't necessarily grasp the deep underlying feature relationships that define the task in a general way. It learns the observed distribution, flavor P, incredibly well. But it struggles to truly generalize to novel patterns, flavor Q, especially if those spurious features it learned don't hold true anymore.
And chain of thought makes this worse.
In the ode case, often yes. They found COT showed consistently negative shot slopes in some ode scenarios, meaning giving it more examples actually hurt its performance on the different test data.
More examples made it worse. How?
Because more examples just reinforce its reliance on those specific, potentially spurious statistical associations it learned from the initial prompt distribution. It doubled down on the wrong patterns for the new situation.
Wow. That really underscores this idea of overfitting to the prompt.
It does. It highlights an over-reliance on learned associations rather than a fundamental generalizable understanding.
And you mentioned one more quick but important point about just measuring performance.
Oh, right. Yes.
Yeah.
They pointed out that how you measure success matters a lot. For instance, sometimes the models produce outputs that aren't even valid for the task, like garbage output.
Parsing errors, basically.
Exactly. And whether you count those parsing errors as learning failures or just ignore them can significantly change the perceived capabilities. Sometimes ignoring them can mask problems, like making Kuti look less sensitive to ode shifts than it really is.
So transparency in how results are reported is key.
Absolutely crucial for truly understanding what's going on.
Okay, so let's try and wrap this up. What does this massive deep dive really mean for you listening, for our understanding of LLMs going forward?
Well, I think the big picture is this. Yes, in-context learning does technically, formally count as learning within a mathematical framework,
Okay.
but it comes with some very distinct behaviors and some really significant limitations. LLMs are incredibly powerful pattern deducers, especially if you feed them enough examples. But their ability to truly generalize, to handle completely unseen tasks or data that looks different, it's just not as robust or consistent as we might intuitively assume, or the hype sometimes suggests.
So powerful, but maybe brittle in ways we don't always appreciate.
Exactly. And the critical takeaway, I think, for both researchers and anyone using these models in practice is caution and transparency.
How so?
Just testing a few prompts, or only using examples that look very similar to your test cases, that might give you what the paper calls spurious performance observations, results that look good but aren't really representative of robust learning.
Right. You might fool yourself into thinking it's more capable than it is.
Precisely. To really understand an LLM's learning capacity, you need robust testing. Multiple prompt styles, varying numbers of examples, including many examples, and crucially, testing on diverse input distributions, especially ones designed to be out of distribution.
Test the boundaries, basically. Don't just stay in the comfort zone.
You got it.
Okay, so this study leaves us with a really provocative final thought, doesn't it? We're seeing this next generation of LLMs coming out, often marketed as reasoning models, sometimes with things like chain of thought capabilities baked in more deeply.
hmm That's the trend.
So the question is, will these newer models truly overcome the limitations the study highlights? Will they become better generalizers, maybe acting more like those powerful push-down automata with real memory and adaptability?
Or will they simply learn to leverage even more complex, spurious features from their training and prompts, getting better at pattern matching within known distributions, but still struggling with true, robust generalization when faced with the genuinely unexpected?
Better mimics or better thinkers?
That's the question. It's definitely something to keep a close eye on and ponder as these incredible technologies continue to evolve so rapidly.